All right, here we go. So this is a follow-up from yesterday. So we are throwing. We got a 12 kilogram cart. We got 8 kilograms of fuel being thrown off at 10 meters a second relative to the cart. Okay, so our initial momentum is 0. Final momentum is still equal to 0, but it's equal to this expression here. This is what we did when we were throwing the shot puts off. Okay, solving for that, you find that the cart now is moving at 4 meters per second. Okay. Shame. Now, if we divide our load in half and throw 4 kilograms at a time, here's our initial throw. Okay. And we find it's now going 2 meters a second. Okay. And then we throw the second, we still throw it at 10 meters a second relative to the cart. Okay. The cart now is moving though. And the consequence of that is we're now moving at 4.5 meters a second versus 4 meters a second. Okay. So does everybody understand the dynamic there? Okay. So
would it take more force to do the second one?
Nope. Nope.
What?
So when
Because right. Okay. So what's the smallest mass you can practically throw off?
1 gram.
0.1 gram. Oh.
Okay. There's not much mass in an electron. So a nuclei, an ion.
Yeah, because the mass of the electron is.
Okay. So throw that one atom at a time would be the most efficient. And this is what's known as an ion engine. Okay, or photon. Oh no, not a photon engine. Not a photon engine. It's like, or they call it ion thrusters. So they're work like they have these. We have these. They just take a really long time to speed up. They put it on Voyager, like the thing that they launched in the 70s. So but the problem is it just takes a really long time to get up to speed. But once you're like, it's the most efficient way to get to speed. Well, because we live in America and patience is not one of the virtues that we esteem. Okay?
You have to leave 2 days before you get on the interstate.
Okay. So,
Is that when we have roots?
there it is.
Okay, the rainfall is vertically, so.
Alright, I go.
Talk to your neighbor. Correct answer is C. Okay. Right. So this has no vertical. Sorry, this has no horizontal velocity. It's adding mass.
It does, however, have horizontal mass.
Okay. Let's see. What am I doing here?
Hopefully, I believe it's like. You don't know. Well, I believe they call it soda bread. It's kind of like.
It looks like
Just like it's like baking soda bread, but I don't know why my mother chose to put it in a pie dish. Can I have some? You want some? Yeah. Sure.
All right.
I'll just give you a small piece. No, it is.
So we know that. Let's see. What do we know? Don't want to do that.
Remember, momentum is constant.
Oh! Oh, it's going so fast. I think it's not. Does it have a skateboard?
Well, let's try this. I'm trying stuff.
It could get close to a star. I feel like that's so much space. I mean, I think no. It's technically impossible.
You're so bad at throwing things. Just do underhand.
Here, do you want some of these? Oh yeah, it's also it's like a little dry, but just like a butter on it. It's calories, that's what it is. Like, it's an important skill to learn. You could just choose to not throw over it.
All right. So B is the root of which. Okay. Yeah, we're close. Okay. So B is equal to the rate at which mass is changing. So if we say time is equal to 0 initially, and there is no rain in the cart initially, the mass of the rain is equal to the rate times the time. And we're sticking that in for here. Okay with that? Sometimes I throw this stuff on the AP test. For real. Okay. Usually, never seen it as a free response yet. It's usually just a multiple choice. Blah, blah, blah. Okay. So this one. So I've got an unbalanced force. We're going to try this. So
Physics, Daniel. What? You like Snickers? Why are you throwing it over there? There we go. No. Hey, Brad, okay? Yeah, he's good. I think he's good. Yeah.
406.
And they probably want to sit on.
can you guys read this? Is this legible?
It is.
So this is B.
Wait, no.
That's not right.
No. Yeah, no, because you did the derivative wrong.
Right. Let me. I need to teach you something before we do this. We'll come back to that. Oh man, I want to come back to that too. All right. All right. So rockets are tough because the mass isn't changing. Sorry, the mass isn't constant. The mass is changing as you lose rocket fuel, as you burn up rocket fuel. Okay. Um, so this kind of falls apart,
DPAT formulation that works.
right? Because the mass isn't constant. Okay. So what we're going to use is net force is equal to the time rate change of momentum. Go with that. So what we're going to do is we're going to do the same thing we did for this problem. We're ejecting fuel at a certain speed relative to the cart, relative to the rocket. The fire comes out, the exhaust comes out at a consistent speed relative to the rocket.
That's
What?
I didn't know that's how they work.
Yep.
That's so cool.
Okay. So here's the cart fully loaded, and as it goes, so it starts out, we're going to say it's not at rest, it's moving at some moment in time, and then a little bit later time, we've ejected some mass, some small amount of mass at some velocity, and this is relative to the rocket, not relative to a stationary observer, but relative to the rocket. Okay, and so the consequence of that is we've gained a little bit of speed. Okay, so the capital M is the mass of the rocket after this is ejected. So here we've got M plus delta M initially. Okay, so initially we've got total mass and the velocity. So we have a certain amount of momentum here. Okay, that's our initial. And then finally, we've got mass ejected relative to the rocket. So to make it work so that the frame of reference is the same, we have to do this thing just like we did here. Oops. That. Remember that trick? Okay. So we're subtracting that speed there. Okay. So this is of this part. This is of that part. Okay. Look at me giving myself just like this. Okay. So here's our momentum beforehand. Here's our expression afterwards. This is the body of the rocket. This is the mass of the ejected fuel. Okay. So when we distribute all this junk, and we bring it all over here, this boils down to this. And if we make delta t, the change in delta t really, really small, you get this infinitesimally change in velocity. So here, these questions are infinitesimally small multiplied by something infinitesimally small. This essentially goes to 0. So what we're left with is the mass of the rocket body times some little change in velocity minus the speed relative, the speed of the fuel relative to the body of the rocket times some infinitesimal small mass ejected. okay, which we can work with. Like that's not crazy, okay? So it was equal to 0 here, so I'm gonna bring this guy over. Okay. So this is the change in momentum of the rocket fuel. This is the change in momentum of the rocket itself. Okay. We put it over, so we know that force is equal to the rate at which momentum is changing. So we put this over delta t. Here's our acceleration, and this is the rate at which fuel is being burnt. Okay. So this is the force of thrust is equal, like here, this is like force is equal to mass times acceleration. Okay. This force of thrust is equal to the rate at which you burn your fuel multiplied by the speed at which the fuel is like pushed out. The velocity, the speed of what, yeah, the velocity which is pushed out. Okay. So the greater the rate of burn, the higher the thrust. And you're throwing more stuff out. Cool with that? Okay. So to find the speed of the rocket, we're going to do these, the separation of variable thing like we did with the air resistance. Okay. So brought M over here, got rid of the delta T's. All right. Take the integral. That's just changing velocity. Over here, you got the 1 over. This is a constant. U is a constant. So it's changing. So you get this expression here for how fast the rocket's going to be going, given how much it burns. Here's your initial and final masses. Okay. So we know this is true. Okay. So the initial momentum of the system is equal to mass times velocity initially. Change in momentum, if your mass is changing, you've got initial mass plus a small change multiplied by the initial velocity times a small change in velocity. Okay. If we distribute all this junk out, we get this expression. Okay. Anything that has before I do that, some of that simplifies. Oh, this goes away. And then we divide by delta t. Here we have really small changes, like if our delta t goes to 0, this expression drops out, and we're left with this. Okay, so we got our initial mass times the rate at which your speed is changing, plus your initial velocity times the rate at which your mass is changing. Okay. So here's kind of the conclusion, and then we'll go back to those examples. Okay, so this is a true statement, regardless if mass is changing or not. Okay, so if mass isn't changing, this is what we're working with up until this point in time. Force is equal to mass times acceleration. If velocity remains constant and your mass is changing, this is a super special case. But
Just learn it.
that's a sure. Okay. But if both the mass and the velocity are changing, then you have this expression. Okay, so you have mass times acceleration plus your velocity times the rate at which mass is changing. Do what?
It's literally just product rule, but yeah.
Yes. Okay. Good with that. So we're going to use this for these problems. So here, so in this scenario, the net force, the next external force is equal to 0. Because we were saying the rain and the cart are part of the system. So the initial momentum of the system is capital M times what's the initial velocity, and then this is B. I'm looking for an expression for this. So yeah, most efficient way to do that. And maybe we shouldn't do this way. It's not seem very efficient. Nope. Whew. It's equal to, let's see if we can break this down into something coherent. We did not show that. First way was better. Do it the way I did first. I don't know why this isn't working out. Final minus initial. T on both sides. Oh, that should be a negative. That didn't help my cause. Lame sauce. All right. I'll work on that. But there you go. Solid end to a semester right there. Good luck, kids. All right. Next time is yours to work on your worksheet. Or